Okay, so we're looking at, this is 4.1F from last day. And we're looking at question number 6. And so we have NH3 and we have HNO3. We have to decide which of those things is going to be the acid and which is going to be the base. Tell me something that you know about NH3, if you can remember. NH3 is present on our table in 2 places. There's one at the very bottom. Whoops, that's the wrong one, not that side, over here. And then there's one up here. This NH3 is on the right-hand side. Therefore, it is what? Acid or base? Base. And it's in the white section, so is it strong or weak? Weak. Anything that's not in a gray zone is weak. How about the NH3 down here? Which side is this on? It's on the acid side. So is NH3 a strong base? Is NH3 a strong base? Nope, because it's on the acid side. Who is the strong base? NH2 is the strong base. Does that mean that NH3 is a weak acid? It is in this gray zone over here. But what do we know about those things in the gray zone? They are the ones on the left-hand side, remember, because the arrow only goes this way, NH3 cannot act as an acid. It is too weak to act as an acid. So the conjugate base of the conjugate acid of a strong base is too weak to act as an acid. Too weak. So it's not an acid, it's not a base. Oh, did I write NH3 as a strong base? That's terrible. NH3 is, oh, I wrote is NH3 a strong base? Oh, NH3 is not a strong base. I was shocked that I had written that, but I was writing a question. NH2 is the strong base, and NH3 is unable to act as an acid because it is too weak. So that means that what kind of a substance is NH3? It is a weak base. So if we go back here, whoops, wrong thing. NH3 has to be a base, which is a good thing because HNO3 has to be an acid, because it doesn't have a negative sign, it cannot accept a proton. So the hydrogen is going to go from the acid to the base. So we end up with then, before we do that, let's check out on our table HNO3. What kind of an acid is HNO3? It is a strong acid, which means it only ever goes in one direction. So it gives away all its protons and it does not take them back. So if I am to write an arrow here, what kind of an arrow am I going to put in here? Yeah, if it's a strong acid, it is going to push that reaction to completion. So the strong acid pushes the reaction to completion. We do not get an equilibrium. And so we would end up with NH4 plus NO3 minus. It doesn't matter that NH3 is a weak base because hydrogen will give all its, or sorry, HNO3 will give all its protons to NH3 and it will not take them back. This guy here is too weak to act as a base because it is the conjugate base of a strong acid. And actually, the fact that we have a strong acid in this equation makes it a little easier to predict whether products or reactants are favored. Who's favored in this reaction? Who do we end up with more of at the end? Products. Yes, because that strong acid pushes it all the way to products. So products are so favored that there's nothing but products at the end. Yes, of course. Okie dokie. Does that make sense, Joanna? Yeah. Anyone else have any questions from 4.1F? All right. 4.1G, we're not actually going to go through the whole thing, but what 4.1G is some vocabulary, okay? And if you've not picked that up yet, there is a new thing in its answer key up there. So on your quiz on Tuesday, this stuff is also on the quiz. In addition to the material in 4.1F, this stuff is also on the quiz. So you should be able to define a strong, what's the pronunciation of that? Arrhenius. Okay, Arrhenius. And Arrhenius, if you remember, is the sort of more straightforward, simplistic version of what an acid and a base are. It's probably what you learned if you were learning about them in grade 10, if you didn't miss that unit due to COVID. Arrhenius acids release hydrogen in solution. Okay, so an Arrhenius acid releases hydrogen in solution. If we're going to say that it's a strong Arrhenius acid, it has to dissociate 100%. That part there represents the part that says it's strong. Yeah? And similarly for a base, the base is these are fairly straightforward bases, not like the ones on that new chart we have. These are the easy ones that you probably learned in grade 10 and 11. The ones that have OH in them, yes? So because these bases, if we want to define one as being strong, it's going to have to dissociate 100%. And if it's going to be an Arrhenius base, it has to release hydroxide. So our most famous acid, HCl, is an Arrhenius acid. Our most famous base, NaOH, is an Arrhenius base. Metal hydroxides are Arrhenius bases, yes? The only little trick with those is that some metal hydroxides have a low solubility, but we still consider them to be strong bases. The only trick is that if you have one of those, instead of using like Kas and Kbs and acid-base math, you're going to have to use a KSP because they have a low solubility to figure out their concentration of hydroxide. Does that make sense? If you've got something that's low solubility, you can use KSP. That kind of question would only occur on a midterm or a final, but it's a perfect question for a midterm or a final because it really says, do you actually know what you're doing? And can you apply things from different units? A weak Arrhenius acid, Arrhenius acid still means it just releases hydrogen. But if it's weak, it dissociates only partially and it forms an equilibrium. So that's the part of the definition that gets to the weak part, that it dissociates partially and it forms an equilibrium. The Arrhenius part is that it releases hydrogen. And similarly, if we have a weak Arrhenius bases, it dissociates only partially to form an equilibrium, but because it is an Arrhenius base, it has that simple, straightforward definition. It just releases hydroxide. Hopefully you're getting good at Bronsted-Lowry. What's a Bronsted-Lowry acid? It donates protons. And if it is a strong Bronsted-Lowry acid, what percentage of its protons does it donate? 100%. Okay? I'm not even going to highlight this one because we're just going to carry on past it, okay? Strong Bronsted-Lowry base. What is a Bronsted-Lowry base? It is a proton receiver or a proton acceptor. And what percentage of its molecules accept protons? 100%, okay? There are only two strong Bronsted-Lowry bases for which you are responsible in Chemistry 12. Those are O2 and NH2, and they are in the gray zone at the bottom left of your table. So notice that there's not very many strong Bronsted-Lowry bases. Most of your strong bases are what type of bases? Most of your strong bases are not Bronsted-Lowry, but Arrhenius. Okay? Most strong bases are metal hydroxides. So most strong bases are Arrhenius bases. Now with acids, it doesn't matter nearly as much. If you have an acid that can dissociate to form protons, then it can donate its protons to water. Yes? So there's no great distinction between Bronsted-Lowry acids and Arrhenius acids. They're all identical to one another. Like HF, you can say, oh, it dissociates 100%, which would make it it dissociates into H+. That makes it an Arrhenius acid. You can say it donates its proton to water, therefore it is a Bronsted-Lowry acid. But with bases, you have those two strong ones that are Bronsted-Lowry, but most of your strong bases only exist in that Arrhenius fashion. They're not really accepting protons. I guess you could kind of say if it makes hydroxide, then hydroxide could accept a proton from water, and you would end up with the same thing you started with. So it's kind of pointless, do you know what I mean, to talk about it in our Bronsted-Lowry sense. Anyway, you can just ignore that if you didn't like that, okay? Weak Bronsted-Lowry acids. They are proton donors, but they donate less than 100% of their protons. And it forms an equilibrium. The Bronsted-Lowry base accepts protons, but if it is weak, it accepts less than 100% of the particles accept protons, and we get an equilibrium. Do you remember, without looking at it, the definition for a conjugate acid-base pair? They're on opposite sides. What else? An acid will turn into its conjugate base form after giving up a proton. Joanna, yes? Yeah, so if you take what you said and you put it into sort of like a formal definition, if you will, it's that you've got two species and they differ by only one proton, okay? So that is a conjugate acid-base pair. What does it mean to be amphiprotic? You can be both an acid or a base. You can both do what? Accept protons or donate them. What do species have to have in order to be amphiprotic? An H and a negative. Okay, good. Except for who? Water. Water is good. Do you guys know the term monoprotic acid? Or is that new? Or it's a little rusty maybe. Maybe it was from before, but we forgot. Mono, what does mono mean? One. And so if you have monoprotic, how many protons do you have? You have one proton. So you can see HCl, CH3COOH, HNO3, and HCN. While we're here, what about these hydrogens here? They cannot dissociate. They're undissociatable hydrogens. Yes. Okay, I want you to imagine that you have a burette. Okay?
Yeah, okay. Your initial volume of the silver nitrate is 18.20 mils.
Yeah.
Now you drip, 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 drip. And now you measure it again.
Yeah.
And now you have 27.22 mils is the measurement on there.
Oh,
okay.
I'm thinking of it.
Okay, so unless, and especially this occurs a lot in organic acids, only the hydrogen on the COOH can dissociate. You should also be aware of diprotic acids. How many hydrogens do they have? 2. Shocking, yes? And it's pretty straightforward, yes? And if we have something that is triprotic, how many does it have? 3 protons. There's not very many of those. There's H3PO4, there's H3C6H5O7. Now we might also use the term polyprotic, and that means it can supply 2 or more protons, which I believe I tried to look up if there was a tetraprotic acid that had 4, but I could not find one. So I think if it's polyprotic, it means it contains either 2 or 3. It's just sort of a more generic term, so it would include the diprotic and the triprotic. Okay? You guys are aware of the hydronium ion? You would be able to write the word hydronium. You would be able to say the word hydronium. You would be able to write the species. Okay, try it. Say hydronium to your partner. Write down the word hydronium, just anywhere you can, and then write the species that is hydronium. Go to 4.1H while we're waiting for that. And hopefully this one is the same. Strong versus concentrated and weak versus dilute. Are you familiar with those differences? So what does it mean if an acid is strong? It's 100% ionized. Does that mean that it is concentrated? No, because you could put in a very little bit of acid and still have it ionize 100%. So you can have a dilute strong acid or a concentrated strong acid. Same thing with weak. Weak doesn't mean dilute. Weak means only partially ionized. And then we want to talk about conductivity. In general, strong acids are more conductive than weak acids because strong acids are 100% ionized. Weak acids typically only ionize about 1 to 10%. So think of it this way, at the same concentration, so many of you are looking like other places and not looking like you're paying any attention at all. And if that's the case, I don't want to be like reading this out to you when you could read it at home for yourself. Yes, because that makes no sense. If weak acids only dissociate 1 to 10%, compared with strong acids that dissociate 100%, about how many times more concentrated is the hydrogen ion in a strong acid of the same concentration? Strong acids dissociate 100%. Weak acids dissociate between 1 and 10%. Somewhere between 10 times more concentrated and 100 times more concentrated. Yeah? Of the hydrogen ion. And so you can see in terms of conductivity, here would be a strong acid, right? Because all the particles are ionized, there's a lot of conduction, and you can see the light bulb is lit up quite brightly. And here we have an acetic acid solution where out of our 3 particles, only one of them is dissociated, which is probably even a higher percentage than it would be in reality, but otherwise we'd have to draw a lot more particles. Okay, and you can see the light bulb is lit up much less brightly. So in terms of conductivity, whether you are strong or weak usually matters more than if you are concentrated or dilute. You can, however, make a weak acid be as conductive as a strong acid. What would you have to do with your strong acid and your weak acid to make them have the same conductivity? Tell your partner. What would you have to do to make a weak acid and a strong acid have the same conductivity? Does it make sense that you would have to take that strong acid and do what with it? Dilute it a lot, yes? And you'd have to take the weak acid and make sure it was very, very concentrated, and then you might stand a chance of them being the same conductivity. I included this. This was actually from grade 11. So, and I included it partially because I just really liked the little pictures because they were cute. But it also had some information. If you're interested in knowing your strong acids by heart, there are a couple of mnemonic devices there. Chloe Kleiberson. Chloe Kleiberson. Oh, next page. Next page. See, we've got Clo, ClO4, and then Cl, and then I, then Br, then SO, and then N. So Chloe Kleiberson. Yes? Or you can do so I brought no clean clothes. If I wanted to do that, I'd put them in the opposite order, right? No, not the opposite order, but in a different order. So if you're interested, you can learn your, that could be handy in university. Probably not here though, because here you always get to have your acid table. I have this in here because AP, they do have to memorize their 6 strong acids. And really, I think what I wanted to point out is that in weak acids, and I was too lazy just to excise this part of it. Oh. In weak acids, the equilibrium lies far to the left. Yes? In weak acids, far more of the acid is undissociated compared with how much is dissociated. Yeah? And that's why your Ka expressions are all like 10 to the negative 5, negative 6, negative 7, because the products are so much smaller than the reactants. Yes? Okay. So if you look at that beaker, it does give you a fairly decent representation. How much is actually dissociated? Not very much. Most of it is together. That's going to become important later on, because later on we are going to simplify our math by assuming sometimes that the concentration of the undissociated acid is just equal to the amount of moles of acid that we put into the water. And we assume that the amount that dissociated is not big enough to make a difference in its concentration. But we'll talk more about that in math unit. Okay, this is just more blah, blah, blah. Feel free to read it. Strong acids are strong electrolytes, weak acids are weak electrolytes. There's some lovely pictures there. Again, this is more for like an AP course, which I'm teaching next semester, so I included it. You don't need to memorize the soluble metal hydroxides, because you will have a table of solubilities. But if you're interested in, and if you're in university and you need a mnemonic device, you can always be like, oh, where was that thing? Or you can email me and be like, hey, Ms. Spence, where was that little mnemonic device? Because I've lost it. Okay, so all of these ones are our soluble metal hydroxides. Yes? I'd rather you emailed me. Because quite frankly, chances of finding me here are like dodgy at best. Do you know what I mean? Like I have people come back and like they're like, I came like earlier this year and you weren't here. And I'm like, oh, sorry. Yeah, but if you want to email me, it's okay. Yeah. Okay. Strong bases dissociate completely in water. We talked about that. Now, just one last thing, because I noticed a few people were having issues with this. Do you know the difference, how to tell the difference between a base and an alcohol? They both contain OH. Bases, the hydroxide is paired with a metal cation or ammonium, and we have an ionic bond. Yes? So we have the hydroxide ion, we have some kind of cation, and in between the two we have an ionic bond, and that is a base. So that would look like NaOH, NH4OH, CaOH2. Yes, those are bases, because you have a cation and you have hydroxide. In an alcohol, we have, instead of a hydroxide, we have this right here is called a hydroxyl group. If you're taking biology, you might have heard that before. Okay, that is a hydroxyl group. And I don't know why the covalent bond is way over here. It should be like here. It should say covalent bond. I guess my tabbing didn't work very well. Okay, so right here, that's our covalent bond. And because that bond is covalent, that hydroxyl group does not break apart. And so these do not dissociate. They just stay intact. Okay, so alcohols are molecular. Yes, they are covalent. Whereas bases are ionic. So if I took an alcohol and I dissolved it in water, do we remember doing this in the past unit? Where if you've got an ionic compound, which bases are ionic compounds, at least the Arrhenius bases, they dissociate, whereas the alcohols, which are not made of ions, do not dissociate. Okay? Weak bases are exclusively Bronsted-Lowry bases. They're weak electrolytes. They're on your table. I don't know, like we've been over this before. But once again, this is another process where the equilibrium lies heavily to the left. That means there's far more of this and much less of these. So when we write a K value for this, and because it's the K for a base, we will call it the KB, okay, which is the KEQ for a base. If we don't have very much of the ions, is KB going to be large or is KB going to be small? Yeah. Okay. Strong electrolyte, weak electrolyte, non-electrolyte. Like I said, I sort of included this because I didn't have enough time to edit it. So if you want to do the exercises, you can, but I will not require it. Okay? This is optional. 4.1i is for homework. Okay, because it's just practice problems. But before we do that, I'm also going to teach you 4.2a. 4.1. Quiz on Tuesday is just 4.1. There will be a quiz on Friday, that Friday on 4.2, which is a fairly short little thing. It's just pH. So we're going to cover this like today and Monday. Okay? And then we'll add some other stuff on that won't be quizzed until after the break. We're just moving along. Tick, tick, tick. Sorry. Okay. The pH scale. As hydrogen, are you guys familiar with the pH scale? Did you ever learn it? Yes? Okay, good. Sort of. Okay. It is a measure, the pH scale is a measure of the concentration of hydrogen ions. That's where the H in pH comes from. Okay? And there's something that's a little bit weird about it, and we'll learn more about that as we go through some of this, is that as the hydrogen gets higher, concentration of hydrogen gets higher, the pH actually gets lower. Okay? Something else that's a little bit weird about pH is that each number on the pH scale represents a 10 times change in the concentration of hydrogen ions. So if you go from pH 7 to pH 6, you have increased concentration of H plus 10 times. If, on the other hand, you've gone from 5 to 3, you've increased concentration of H plus 100 times, because for it would be 10, and then 10 squared is 100. Yeah, 10 times 10. And I think we touched on this earlier, to have a very low pH, you can either have a strong acid, because strong acids dissociate 100%, or you can have a very concentrated weak acid, okay? It must be at that high concentration to produce a large pH. And this kind of just says a bit more. I thought the pictures were cute. So let's look at our table here. So we have our acids, the alkalis, which are also, this is a British resource, so they call them alkalis. That's the more common term there, but we call these bases more frequently. So you have the acids, the bases, and the pH scale. So you can see that alkaline pHs, or basic pHs, range from what to what? 8 to 14. And in fact, not just 8 to 14, anything greater than 7, okay? So pH greater than 7 is your basic pHs. Okay, and in fact, it can go up past 14 too. I know that seems strange because we always hear that it goes up to 14, but it can go past 14. Neutral is pH 7. That would be water, pure water. Okay. Pardon me? No, there's other things like salt water is neutral. Okay. And then acidic is pH less than 7. So if you had 6.99, that would be very mildly acidic. Yes? So anything less than pH 7 is acidic. And it can actually go lower than 0. So you can notice here, and this will come in handy for a question later, there are, what do you see over here? We got like fruits and juices. Then we have stomach acid and battery acid. What kinds of things do we see up in the, bases? Soap, bleach, drain cleaner. What kinds of things are we looking at here? Lots of cleaning products, yes? When the pH is high, what do you notice about the hydrogen ion concentration? It's low, yeah? When pH is low, the hydrogen ion concentration is high. Now we got one other thing on here, and that is our hydroxide ion. What do you notice about its concentration when the pH is high? OH is high. So basically hydrogen and hydroxide go opposite one another. The more you have of one, the less you have of the other. Yes? And they all change by, what's the change here? It's always changing by a power of 10. Yes? And this one, it would be dividing by 10, okay? All right, so you can refer to this table at any point if you want to. As the pH increases, what happens to hydrogen? Decreases. As pH decreases, hydrogen increases. This worksheet is a lot about just making sure that you get that opposition straight in your head. You'll notice there's a lot of repetitive questions. When you do this worksheet, I would actually recommend not doing it all like in one sitting, but maybe do like the odd questions and then go back and do the even questions later so that you've split it up so that your brain retains the information better. H plus, as H plus increases, what happens to OH? It decreases. As H plus decreases, OH increases. pH is what we call a logarithmic scale, which means that if pH doubles, does the hydrogen concentration double? No. For every change in the unit of pH, hydrogen ion concentration changes by a power of 10, or a factor of 10. Now, what if we increased pH From 2 to 4. Well, if pH is 2, what's the hydrogen ion concentration if pH is 2? It would be 10 to the, you can look it up. Go look it up. What is the hydrogen ion concentration if pH is 2? 0.01, which is 10 to the what? -2. So that's going to be 0.01 molar. If pH is 4, go look up what the hydrogen ion concentration is. It's 10 to the -4, and so that's going to be 0.00001 molar. The pH has done what? Sorry, yes. Yeah. pH does not have a unit. No. Has pH increased or sorry, no, this should say hydrogen ion. Has hydrogen ion concentration increased or decreased? It decreased, it went down. So pH went up, hydrogen goes down. And pH went up by 2 units. And therefore concentration of hydrogen is going to go down by a factor of 10 to the 2. In other words, 1/100th. Yes, so it's decreased by the factor of 1/100th times. Yes? I'm sorry. Yes, you're right. Where did that come from? Yeah, no, there should just be one there. Thank you. So what if the pH of a solution decreased from 7 to 4? What happened to our hydrogen ion concentration? First of all, is hydrogen going up or down? Hydrogen increased. And then we can say by a factor of 10 to the power of 3, because the difference here is 3. Yes? When you're asked a question like that, in general, you won't be asked to show your work. Usually it'll be a multiple choice question. So don't worry too much about showing your work. Yes, of course. So it's 1,000 times or 10 to the 3 times. There is another scale, and it is the POH scale. Guess what? We had a pH, we also have a POH. And what do you imagine it does? It's all the opposite. So when you are the most acidic, that means your hydroxide ion concentration is very low, but your POH is very high. Yeah, so the more acidic you are, the higher your POH. The more basic you are, the higher your pH. Okay? I know, it's a little bit like mind-bending sometimes. That's why I'm going to ask these questions over and over again. Okay? So if we look at this, actually, here's something else we're going to point out to you. At the same level of acidity or basicity, what is the sum of the pH and POH always equal to? So go through and try adding up a few of them. $14, right? So it is always true, at least at 25 degrees Celsius, the pH plus the POH is equal to what? 14. And this value here is known as the pKw, where Kw is the KEQ for the dissociation of water. Don't worry about the details there. What you're really concerned about today is this. I'm just introducing these terms so that next class they aren't so unfamiliar. You are not expected to really understand pKw or KW today, all right? What you are expected to take away today is that pH plus POH equals 14. Okay. Yes? Huh? Oh, we have to say at 25 degrees because it changes. If you have a higher temperature, it won't be 14 anymore. It'll be a different number. So it's a different number at different temperatures. Huh? Yep. Yep. And we'll talk about it in terms of Le Chatelier's principle. Ooh. We'll put our heat term in. We'll see which way it shifts to the reactants or products. Yes? Okay, but not today. All right? Now, if we take a look at our concentration of hydrogen times our concentration of hydroxide, what do we get if we multiply these things? We add the exponents, and so we would get 10 to the negative 14 and 10 to the negative 14 and 10 to the negative 14. So concentration of hydrogen times concentration of hydroxide at 25 degrees Celsius is equal to, and I'm going to stick a 1 in here, 1 times 10 to the negative 14. This number right here, that's Kw. And what was Kw? It was the KEQ for the dissociation of water. We are almost out of time. So what I'm going to do is I'm actually going to record the rest of this because I would like you to actually do the questions on here over the weekend. So I will record, so watch the recording of the rest of this worksheet. There's not a lot more to it. And then do the questions I ask you to do. I won't get you to do all of them because, like I said, it's going to be better if you sort of, do some of them now and then do some of them on Monday or whatever. Okay, so maybe to get you to do a third of them now, a third of them on Monday, a third of them on Tuesday or something like that. Okay? And do the assigned questions. The video should be up by tomorrow morning. Is that soon enough? Anyone going home tonight and is like, I really, really need to watch chemistry on Friday night? No? No? Nobody's dying for that? Okay, so I will have it up by tomorrow morning then, okay? Hi. Yes. Uh-huh. It is possible. I've had this problem before and it always makes me unhappy. We got HSO3, and we have CH3CO minus. Okay, and we have SO3 2 minus. Here. Oh, sorry. HSO3 is here.